Well, hello, welcome to another video. This is what we're going to call physics in the forest. We're back in school, sort of, and it's too noisy at school to try and do this. And at home on Mondays, my daughter's there, and so that's too noisy. So I thought, oh, why not? We'll come out into the forest and shoot a physics video. Turns out the logistics aren't quite as simple as I'd anticipated. I don't have a chair or a table. It's nice out here though. I hope you enjoyed the sounds of the birds. They're not digitally mastered afterwards. They're authentic. Here we go. Special relativity. So this is an interesting topic. Einstein came up with it. It's what he's most well known for, though it's not what he won his Nobel Prize for. So at the end of the 1800s, the physics community essentially figured they had everything all ready to go, a couple more things to deal with, but otherwise we've got it sort of set. And then they discovered that the nucleus was made up of positives and the electrons were on the outside. And the problem with that, of course, was that at that time they weren't sure why the electrons didn't just orbit right into the middle of the nucleus and annihilate itself. Similarly, they weren't sure if all the protons are in the middle, why didn't the protons just explode? And so at this point in physics, we essentially have four known forces. We've got gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. And so Einstein kind of went back to what's called first principles, where he said, what are the things in physics that I know for absolute certain? And I apologize for the size of this font, it's tiny. On the website it should be expandable. So the first thing he said is, I know about the principle of relativity, and that is all laws of physics in non-inertial reference frames, we'll talk about that in a minute, hold true, and there's no preferred reference frame. So in other words, you could pour a cup of coffee in your house, and it's the same as if you're in a plane traveling at 500 kilometers an hour. Of course, provided there's no turbulence. But that's acceleration, the turbulence bouncing up and down, and so that means it's a reference frame. I'm just thinking it might actually be inertial reference frames. Not super important for our purposes, but if you look back at these later, I don't know why you ever would, but if you do, that might be wrong. I think it has to be inertial reference frames. The second thing is easier to understand, the constancy of the speed of light. So the speed of light in a vacuum, or I've had this problem a few times, in the absence of anything, so in other words, in outer space. It's always the same regardless of who emits the light and who receives the light. So, and that's different than a few things like, let's pretend we're running with a baseball. If we're running towards somebody with a baseball, if we're running at 10 meters a second, and if I could throw at 15 meters a second, I can't throw at 15 meters a second, then if I threw it to somebody, they would receive the ball at 25 meters a second. Whereas with light, if I'm running and I hit the button on a flashlight and I emit light, the light that the person receives who's stationary is just going the speed of light, 3 times 10 to the 8th meters a second, or in physics we just call that c. A reference frame, that's really important. We're going to talk a lot about reference frames here. I'm just trying to decide where I can put my hand without putting it on prickles. So a reference frame. People who have the same velocity, speed, and direction are in the same reference frame. So right now I'm sitting on a rock on Cobble Hill Mountain. Anybody else who is stationary with the Earth, they're in my reference frame. And similarly, I'm in their reference frame. For the people driving on the highway, we're in slightly different reference frames. They're traveling at a velocity relative to them. I'm not. Different reference frames. Now our reference frame differences are really minor. 100 kilometers an hour, 500 kilometers an hour, all of the things we talk about today, they don't apply to these speeds. For all this stuff to work, the speeds have to be close to the speed of light. They typically say about 10% of the speed of light, which is 3 times 10 to the 7th meters a second. Incredibly fast. So we're going to talk about things, and you'll kind of go through them and like, yep, that makes sense, that makes sense, that makes sense. Then we'll draw a final conclusion, and you'll go, whoa, that's not at all what I expected. So here we go. It says here, Newtonian mechanics, that's what we've been studying things usually at really low speeds. Works well for slow speeds. When relative speeds get up to 10% the speed of light, our classic equations break down. So we're going to have a little thought experiment here. This is too small to write it on, so I'll do it on this piece of paper here. So here's what I want you to imagine. I want you to imagine we've got a train car. Here's the train car. And these are going to be ridiculous things to think about, but they're sort of important. And somebody in the train car has a flashlight. And the flashlight is going to send a beam up to the ceiling. There's a mirror there, and then down to a sensor attached to a computer. I know you're probably all amazed at how much my art's improved. And the flashlight and the sensor are joined together so that the computer can figure out how long it took the light to go from here to here to here. Now, to make things easy, I'm just going to say that we'll use big numbers. We use like seconds. I mean, it's ridiculous. It's not, seconds is no good, but it just makes it easy to talk about. So let's pretend we do this. So we go, okay, so this person here goes, the light goes this distance, and then we know the speed of light's always the same, and so we can figure out the time, and the computer verifies the time. So the person on the train here goes, oh, I'm going to try a comic bubble. I'm not sure I've done those before. 3 seconds. Obviously, that's stupid big. It's massive. And there's people outside the train watching this experiment. That's us. Let's pretend we're outside the train. We're watching this experiment. And we've got to think about a couple of things. So first of all, again, this is ridiculous because the train would have to be going like this fast. 3 times 10 to the 8th is 3, 1, 2, 3, 4, 5, 6. It'd have to be going like that fast, which is how many? So that's 30,000 kilometers a second fast. So we wouldn't see anything. But we're going to pretend we do. We'll pretend the side of the train has got plexiglass on it so we can see in. Now, the first thing I want you to think about is what it looks like to the people standing out here. It doesn't look to us like the light goes to the top of the train and down again. It will look like to us, because the train's moving sideways, it'll look to us like the light goes up like this and down over here, because for us the train is moving past, and so the train, I'm sorry, but this is not going to be the same train car. It's supposed to be the same train car, but it won't look the same. It's like this. Oh, this is just terrible. My greatest fear today is not whether you understand it or not, it's whether or not I get caught up here doing this, because I don't know how I would explain what I'm doing. Anyway, so if we look at this, here's what we would say. We would say, oh, the light traveled this distance, obviously a much bigger distance than this, and the speed of light is the same for both the person on the train and us. So we'd say, oh, that took 5 seconds for the light to leave the flashlight, hit the top of the ceiling, and go back down to the sensor on the computer. And that's like the first time. Oh, I'll do the speech bubble around it. Ooh, look at that, 5 seconds. And that's the first time for us where we've seen differences in time. It doesn't matter whether you're driving on the highway and you compare your watch to somebody at home, the times are all the same. But when speeds get really, really big, if you start measuring times outside of your reference frame, then they start to change. So here in this question, they're in 2 different reference frames. This person's moving, this person's stationary. The event, the light going from the flashlight to the ceiling back to the computer, occurred in this reference frame. When these people measured something outside of their reference frame, they found the time to be different. So back to this sheet with tiny bits of paper. There's a formula for that. It's called time dilation. So when time is measured in a different reference frame, the different reference frame is crucial. It moves more slowly. Here's the formula. T equals T0 over the root of 1 minus V over C squared. So these 2 things are the important bits. The math on this is really simple, but it's just determining whether the thing you're given is T or T0. So T is the time for an event to occur as measured outside of the reference frame of the event. t0 is called the proper time, or the time it takes an event to occur as measured in the reference frame of the event. V is the relative speed between the reference frames, and c is the speed of light. So here's the first example. James is on a train traveling at 2.75 times 10 to the 8th meters a second. We are watching him. James times how long it takes him to eat dinner, and he says it takes 3.4 minutes. How long do we say it takes him? So here we go. This is our first example. One, so here's what we've got. We've got V is 2.75 times 10 to the 8th meters a second. Now he says it takes him 3.4 minutes. He's doing the eating. That 3.4 minutes is in his reference frame. That's T0. That's your big decision on these questions. 3.4 minutes. Now the great thing about relativity is that you don't need to convert any units. I'm going to leave it in minutes. My answer will be in minutes. Makes it kind of easy for us. And so we'll put it in the equation. So here's the equation. T equals T0 over the root 1 minus V over C squared. And it's going to look like 3.4 over the root of 1 minus 2.75 times 10 to the 8th over 3 times 10 to the 8th all squared. I'm going to grab my calculator. I apparently have lost my calculator. My phone, I guess that is. Hang on. So, when calculating this, I suggest using lots and lots of brackets and doing it as sort of easily as you can. So, here's what I'm going to do. Let's see. With this calculator, I'm going to do the bottom. So the root, there's a bracket, 1 minus bracket. Notice the 10 to the 8ths cancel, so no need to deal with those. 2.75 divided by 3, close the bracket, squared. Let's get that answer. Oh, apparently I didn't put a bracket in where I was supposed to. Close the bracket. There we go. So I get 3.4 divided by 0.39965, and I get, let's go 3.4 divided by that answer. Oh, that's not right. 3.4 divided by 0.39965, I get 8.51 minutes. And so for an outside observer, we say it takes him longer. We say it takes 8.51 minutes. And so hence the name time dilation. Time's getting bigger. Okay, so number 2, the example number 2 here, it says, James is still on the train, but it's now traveling at 0.97 C. He looks out the window and sees us eating dinner. He says it took us 18 minutes. How long do we say it took us? So one important thing to realize here is the speeds are given differently. It's easier when it's given in this form, and I'll show you why in just a second here. Okay, so example 2. We have got a new speed, 0.97 C. Now here's the reason this is the second example. Still James on the train, but we have to think about the time. So he says it took us 18 minutes to eat our dinner. And that means he's measuring something outside of his reference frame. So that 18 minutes, T, is right there. It's not T0. He's measuring something outside of his reference frame. And so again, we'll use this equation. So we'll get 18 equals T0 divided by the root of 1 minus 0.97 C over C squared. And notice the C's cancel, and it's very easy to figure out. I'm going to keep going here with this. 18 equals T0 over the root of 1 minus 0.97 squared. And that's 0.243. We'll 0.243 by both sides. Get T0 equaling 4.38. So we say it took us 4.38 minutes to eat our dinner. Okay, I think that's it for the first part. Next week there'll be another video on length and mass. For that, we'll leave it. There's some questions up for you. I don't think they're going to take you a long time. As I said, the hardest part is going to be for you to figure out what T and T0 are. All right, thank you. Good luck this week. Let me know if you have any problems.